This is the Fields Homework Booklet, question 25. Explain why the mass of an object is constant, but its weight may change. You can see here that there are 3 marks allocated to the question, and it is fairly clear that you ought to be commenting on both the mass and the weight, and then linking that to the difference between them. So mass tells us about the amount of matter present within something, and that's independent of position. However, the weight of something is a force calculated by multiplying the mass by the gravitational field strength. So that means the weight depends on the gravitational field strength. Finally, you need to explain that the gravitational field strength depends on position. So it would be good to comment that it varies with distance above the Earth, or perhaps that it's different for different planets. Next, you have a table giving values for the gravitational potential at 3 different distances from the centre of the Earth. So here you have the left-hand column giving distance from the centre of Earth and the right-hand column giving the values for gravitational potential. First of all, you're asked to explain why gravitational potential at a point in a field is always negative, as we have seen here. So the key point is that gravitational potential is 0 at infinity. This has actually been a choice by definition made by physicists in the past. So if the gravitational potential is 0 at infinity, and we have to do work to move a mass towards infinity, because we're working against the pull of the gravitational attraction of some mass, then doing work increases potential and increases potential energy. So in this context, you're increasing the potential from a negative value up to 0. So next you need to show that the data in the table is consistent with the expression that the potential is inversely proportional to the distance from the centre. So you would write that in this format here, and then if the potential is proportional to the reciprocal of r, then it equals a constant divided by r. This means that the potential times the distance from the centre r must be a constant. So quite simply you need to test that out for the data given. So this part is just a copy of what was in the table, and all I have done is multiply the pairs of values to give these 3 answers. Finally, it would be good to comment that these 3 values are approximately equal. Now a calculation. So you're told that a satellite has a mass of 450 kilograms, and it's moved from an orbit of radius 7,500 kilometers to a higher orbit of 12,500 kilometers. The question says, use data from the table to show that the potential energy of the satellite increases by about 10 gigajoules. Very, very important that you use the data from the table. It also makes life pretty easy. So first thing is to look at the 2 values in your table of the 2 heights. So we had 7,500 kilometers, and we have 12,500 kilometers. So we're taking the 2 values from the table there shown. And to have a change in potential, it makes sense to calculate this using the final value, take away the initial. So we have minus 3.22, take away minus 5.36. Each of those multiplied by times 10 to the 7. Very easy to miss that in the table heading, so take care whenever reading tables or graphs that you look very carefully at the labelling. This gives us a value for the change in potential, in gravitational potential. However, you were asked for a change in potential energy. So to convert from a change in potential to a change in energy, you simply need to multiply by the mass of the satellite. So that's what I'm doing here, leading to an answer of 9.63 times 10 to the 9 joules. Now the question said you needed to show it's an increase of about 10 gigajoules. I guess it could be worth just putting a final statement that this is approximately equal to 10 gigajoules. So 10 to the 9 corresponding to the prefix giga. Now a question relating to energy. So the kinetic energy of the satellite orbiting the Earth with a radius of 7.5 kilometers is given as 12 gigajoules. You are asked to calculate the kinetic energy of this same satellite when it is at the higher orbit that we've previously considered. So you may think, first of all, that kinetic energy is given by the equation 1/2 mv squared. You will then realise that you haven't been given a value for the speed in this orbit. So you need to think of any relevant equations to do with orbits that would enable you to bring in the variable of speed. So that is achieved by relating the general equation for centripetal force, mv squared divided by r, to the equation for the gravitational force of attraction. Tidying up that expression and rearranging gives you the equation for the speed of a satellite in orbit. Well worth being aware of this equation and remembering how you can work it out. So now bringing that into the kinetic energy equation, we have 1/2 times the mass times the gravitational constant, the mass of Earth, and the radius of the orbit. Just watch out for those kilometres that you get them converted into metres here. That gives you an answer of 7.2 gigajoules. So notice the beginning part of the question was just a statement that at the other radius you had 12 gigajoules of kinetic energy, and at this higher radius you've now calculated that you have 7.2 gigajoules. This leads us to the next part of the question, which simply asks for the change in kinetic energy when it moves to the higher orbit. So we have got here the final kinetic energy, take away the initial kinetic energy, and that gives us a negative value. So it does mean we actually have a loss of kinetic energy here. Finally, the question asks you to calculate the total energy that has to be supplied to the satellite to move from the lower to the higher orbit. We already are aware that there is a loss in kinetic energy when you make this change, so now you need to calculate what the gain in potential energy will be. So the increase in potential energy will be the final potential energy take away the initial energy. You'll see here I've gone straight to an equation for energy rather than potential, which is why you're seeing the m in the equation there. So the gm divided by r2 would be the final potential, but putting the mass in there as well makes it the final potential energy. Tidying that up leads to this expression for the change in potential energy, and then you have a lot of careful substitution to do. So the gravitational constant, the mass of Earth, the mass of the satellite, and then a subtraction of 1 over the original radius, take away 1 over the final radius. This leads us to an answer of 9.6 times 10 to the 9 joules, or 9.6 gigajoules. Now, we still haven't finished answering the question here, so we need to look back. We're asked to find the total energy that needs to be supplied to make this change. So we will need an increase of 9.6 gigajoules, but we have got 4.8 gigajoules available from the loss in kinetic energy. That means we will need to provide an extra 4.8 gigajoules in order to make the change. So you could think as the total of the total energy supplied as being equal to the gain in potential energy, take away the loss of kinetic energy. Now you will probably look at the working out that we've done here and think that this is a huge amount of work for 1 mark, and I do agree with you. However, the mark scheme did take a little bit of a shortcut. It required sort of assumed knowledge, which you may have come across as you've practiced this type of question before. If you look back at your kinetic energy calculation, you will be able to see why the final answer is actually equal to the change in kinetic energy. So this was our expression for the change in potential energy. Just look at the variables G, M, M, and then we have the brackets and the subtraction here. And if you go back up to the calculation that we had earlier for kinetic energy, you will see that the kinetic energy has the term mv squared in it, but v squared was gm divided by r. So you can see once again you have got a g, an m, and an r, and if you have a subtraction you're going to get a very similar notation. So you could prove to yourself that the final answer would be numerically equal to the change in kinetic energy. I think this is a lot to expect though, so I'm quite happy for you to learn the longer method at this stage and hope more marks would be allocated.